A paired t-test for the mean. Here we have two samples, but these are not independent samples. In a different video, I'll go over testing for difference of means for independent samples. But here we have 20 patients, and we have for each patient we have a cholesterol level before and after a 6-week vegetarian diet. So for Abe, the cholesterol level was 260 before the diet and 220 after diet. For Barb, 320 before and 200 after, and so forth. And what we're going to do here is instead of treating these as two independent samples, we're essentially going to treat this as one sample. We're going to subtract the before minus the after. So 260 minus 220 is 40. 320 minus 200 is 120. Cindy's cholesterol level actually went up from 240 to 260. So that's 240 minus 260 is negative 20, and so forth. And so we'll get a single number for each patient, and then we'll use that to for our hypothesis testing. So the mean difference was 34.5 milligrams per deciliter. So on the average, the cholesterol level went down 34.5 milligrams per deciliter, and the standard deviation was 29.1 something. Okay, so we want to test whether the diet was effective or not. So if the diet is effective, then the cholesterol level should go down. So the mean difference should be greater than 0 if the diet is effective. Mu naught will always take as mu equals 0, although some textbooks will have greater than or equal to 0, but in either case equal is included. So we'll say the diet is not effective if the mean difference is 0, and the diet is effective if the mean difference is greater than 0. So mu d is mean difference, expected cholesterol change in the long run if everyone in the entire patient population adhered to the diet. So so for our critical value, we'll use the using critical value method here. We have 20 patients. 20 minus 1 is 19, and our desired confidence is 95%. That leaves 5% doubt. So we want to look in row 19 and 0.05 of the t-table. If it'll be some tables will have a one-tailed column and a two-tailed column, but we want the one-tailed column, 0.05, and row 19. And so 105, it's 1.72913. 1.72913. Okay. I think the table of the book doesn't carry quite so many digits, approximately 1.729. And so that's our critical value. The test statistic, the mean difference, which is 34.5, times the square root of n, that's square root of 20, divided by the standard deviation, 29 point something. That comes out to be 5.301. And because our test statistic is 5 point something, is more than our upper critical value of 1 point something, we reject H naught with 95% confidence and conclude that the diet was effective. And we could estimate the p-value. Actually, some of the exercises in WebAssign have links to technology where you can actually compute the p-value. With their table, generally we can't get the exact p-value for from the t-table. The z-table will give us a precise p-value, but the z-t-table is not really set up for that, but we can estimate that. If we look in row 19 of the t-table, here's row 19, our test statistic was 5 point something, and that's bigger than the biggest t-score in the table. So that means our p-value is going to be less than the column heading here. It's less than 0.0005. That gives us an estimate for the p-value, and that's a pretty low p-value. I think if you use the table in the text, their lowest row is 0.005, but using the table in the text, you can only say it's less than 0.005. The table in the course files, we can determine it's even less than 0.0005. But in either case, there's at least strong evidence, possibly very strong evidence, that the diet is effective. Anytime you have a t-score of more than 3 or less than -3, or either a t-score or a z-score, that's is going to provide pretty strong evidence. Some books, to use these formulas, some books require that the sample size n is at least 30, or the variable is normal. Ours does not make those requirements. If the variable itself is normal, then these numbers will be more accurate. Some of the exercises in WebAssign will give you some computer output and ask you to identify some of the statistics from the computer output. And computer output can be a little bit cryptic, but anyway, it takes a little bit of getting used to. But we're here. This is actually from Excel. I put this data into Excel and got this output here. The Microsoft Excel, the spreadsheet. T-stat, that would be the test statistic. That's 5.301. You might recognize that number. The probability that of getting a t-score less than this test statistic is 2.038E05. So that minus negative 0.05. So that means that you move the decimal point 5 places to the right. So that's the p-value. So this actually gives you the p-value of 0.000 2038. So that's a pretty small p-value. That provides very strong evidence. The critical value for 95% confidence is 1.729 something, which we got. That's what we got that number from the table, and that's what we compare our test statistic to. Anyway, those are you'll see some examples of computer output at WebAssign. They'll ask you to identify some of the features, such as what I have circled in red here. Okay, here's another example with paired data. Now, the first example we had first example was doing a test of the sample mean. This will be instead of a mean, we'll have a proportion. This example here, we have a sample of 1,000 patients were divided into 500 pairs matched by age and clinical condition. And one person in each pair was given treatment A, one person in each pair was given treatment B. So this is it's related to the binomial. We have two possible outcomes: either the patient is cured or they're not cured. But the thing is that these are not independent samples. So again, we have in a sense, you could say that there's two samples of 500, but they're the problem is that they're these we've paired these patients by age and clinical condition, so these are not independent samples. So for the patients getting treatment B, 400 out of 430, the B totals here, 430 out of the 500 were cured. For the patient getting treatment A, 420 out of the 500 were cured. But and again, these were not independent samples. So what we want to do here is focus on the outcomes that were different. So in 30 pairs, the patient getting treatment B was cured, but A was not. And in 20 pairs, the person getting treatment A was cured, but B was not. So those are the two numbers we want to focus on for this test here, because they're dependent samples. Okay, so the null hypothesis: response is independent of treatment. Alternative response depends on treatment. And the discordant pairs, NA, 20 pairs where treatment A is better, and B, 30 pairs where treatment B was better. I want to check that NA plus NB has to be at least 20, and 20 plus 30 is 50. That's more than 20. That's a yes. If not, you could use binomial probability. And then we want to compute the test statistic. This is absolute value of NA minus NB, and then subtract 1, square it, divide the whole thing by NA plus NB. So if we put in the 20 minus 30, and absolute value is negative 10, take the absolute value, you get positive 10. 10 minus 1 is 9. 9 squared is 81. So this is going to be 81 over 50. I didn't really show the steps here, but it's 81 over 50, and it's equal to 1.62. So that's our test statistic. And then to get the critical value, we go to the chi-square table. You can look in row 1, column 0.05. So it's chi-square table, row 1, column 0.05. I get about 3.841. Because our test statistic 1.62 is less than 3.841, we fail to reject H0. The sample does not provide enough evidence to say that the response depends on treatment. And that concludes this presentation.